In this class, we deal with domains and ranges of different functions. First of all, what is meant by the domain and what is meant by range? Let us have a just rebrush about our knowledge. If f from a to b is a function, then a is called the domain of the function and the set f of a is equal to the set of all f of a such that a belongs to a is called the range of the function f. Of course, it is a subset of the codomain B. Now, we shall discuss with the domains and ranges of various functions belonging to various models in the present class. Let us consider the function f of x is equal to 1 by x. What is f of 1? 1. F of 2? 1 by 2. F of 3? 1 by 3. F of 5? 1 by 5. What is f of 0? We are not able to find because 1 by 0 is not defined. That is why the point x is equal to 0 is a troublesome point in defining f of x. So it is not possible to find f of x when x is 0. Therefore, the set of all those real numbers for which the function f of x is defined is r minus 0. And we notice this particular set is the domain of the function. Thereby, we can understand and believe that the set of all those real numbers for which f of x is defined properly, conveniently, without any trouble, is nothing but the domain of the function. Therefore, f of x is equal to 1 by x. The domain is r minus 0. Another function, let us observe. F of x is equal to 1 by x minus 2. Then, what is the point which troubles you in defining f of x? X is equal to 2 troubles you. Why? Because f of 2 it becomes 1 by 0 again not defined. Here we notice that the domain of the function is r minus singleton 2. Similarly, if f of x is equal to 1 by x square minus 1, to have the domain of this function, as in the previous cases, we are supposed to remove some real numbers which trouble us in finding f of x. It's very easy. For that purpose, imagine when x square minus 1 becomes 0. Clearly, x square minus 1 becomes 0 when x is 1 or minus 1. Thereby, we trace the domain of the function, of course denoted by df is equal to r minus 1 comma 1. Like this, we will be able to give so many examples for this model. So, to have the domain of the function which belongs to this model, we first notice those real numbers which make the denominator 0, and we shall avoid them to take in the domain. Therefore, the domain here is r minus 1 and 1. Again, one more example. Suppose f of x is 1 by x square minus 3x plus 2. In this case, it is also a very easy procedure to know those points which make this x square minus 3x plus 0. They are nothing but x is equal to 1 and x is equal to 2. Therefore, domain of the function here is r minus 1 comma 2. Why? Because x square minus 3x plus 2, which lies in the denominator of that function, is just nothing but x minus 1 into x minus 2, and those real numbers which make it 0 are 1 and 2. That is why domain of the function is r minus 1 and 2. Let us now consider the function f of x is equal to 1 by x square plus 1. Thinking of it as in the previous case, we first of all should search for the real numbers which make the denominator, that is x square plus 1, 0. It is clear that for no real value of x, x square plus 1 becomes 0. Therefore, 1 by x square plus 1 can be defined for any real value of x. That is, f of x can be defined for any real value of x. No question of getting any trouble for any real number to find f of x. Hence, the domain of f here is just nothing but the entire set of real numbers, and no real number might be deducted here because no troublesome point is available to define f of x here. The reason being, no real value of x can make x square plus 1 0. One more example of this sort we can see again. F of x is equal to 1 by x square plus x plus 1. Here also, to find the domain of x, we surely search for those real numbers which make x square plus x plus 1 is equal to 0. From the knowledge of quadratic expressions and equations, we see that the discriminant of this x square plus x plus 1 is negative. Hence, no real values, no real roots will be there for the equation x square plus x plus 1 is equal to 0. That is, for no real value of x, x square plus x plus 1 is 0. Hence, we find no real number which is troublesome to define f of x. That is, the domain of this function is again entire real number system. No problem at all here also. Therefore, in estimating the domains of functions, real functions, which contain a precise denominator, we look for those real numbers which make the denominator 0 and we avoid them to take in the domain. That is, we delete them from the set of real numbers to frame the domain of the function. Well, let us see another model. Let us notice the domains of some standard, very simple functions. F of x is equal to x to the power of n. N belongs to n. To define this f of x, there will be no trouble at all for any real number. Therefore, the domain is real numbers. F of x is equal to 1 by x. Just now we have seen what is the domain? R minus 0. F of x is equal to root x. What is the case with this? F of x is equal to root x. We all know that this root x may not be defined, cannot be defined if x is negative. Therefore, to see that root x is always defined, we must take care that x is always non-negative. That is, x greater than or equal to 0. X greater than or equal to 0. Hence, the domain must be open interval 0 to infinity. Closed interval 0 to infinity. Even root 0 you can define. Therefore, the answer is, the domain is closed interval 0 to infinity. Whereas, if you look at the function f of x is equal to 1 by root x, here enough precaution is to be taken that root x is defined and not 0. root x is defined but not 0. So in what way should we think of? X must be non-negative, at the same time x must not be 0. It does mean to say that x is strictly positive only. Hence, we notice that the domain of this function is open interval 0 to infinity, or this can also be represented as R plus, in this to mean to say that it is the set of all positive real numbers. Therefore, f of x equal to 1 by root x means it is closed in open interval 0 to infinity. F of x equal to root x means it is closed interval 0 to infinity. Let us see some more functions. Some more functions. Let us have a look over. F of x is equal to e power x. We all know that for any real value of x, we can always find e power x. So, we can find no real number x such that e power x may not be defined. Hence, the domain of this function is the set of real numbers. Again, f of x is equal to log x. You consider. According to the definition of a logarithm, x must be strictly positive. It is not 0 and cannot be negative, hence x must be positive. Therefore, for f of x equal to log x, it is R plus, or this can again be mentioned as open interval 0 to infinity. Open interval 0 to infinity. Another standard function, that is f of x is equal to mod x. We trace the domain of this function is also R. Why? Because for any real number you are able to define mod x. That is, for every real number you are able to define f of x. No question of deleting any real number from the set of real numbers for defining f of, that is f of x. For domain of f, it is R. Well, what happens to the fate of f of x is equal to 1 by mod x? Here mod x lies in the denominator. We have to see that it is not 0. When can mod x be 0? When x is 0. Therefore, the only troublesome point for us to define f of x is x equal to 0. Hence, the domain of this function is also R minus singleton 0. Next one, f of x is equal to integral part of x. This is read as the integral part of x, or the greatest integer less than or equal to x. Greatest integer less than or equal to x. As an example, what do you mean by integral part of 2.3? Observe the number 2.3 on the number line. 2, 3, 2.3. There are so many integers behind 2.3 and beyond 2.3 also. The greatest among all those integers which are less than this is 2. That is why read this 2 as the integral part of 2.3. Okay. Similarly, what is the integral part of 3? It is 3 itself. This is the function integral part of x. For this function, let us imagine the domain. Where do you find trouble to define f of x in this way? We find no trouble at all, at no real number at all. Therefore, domain of this function is again R. What happens when f of x is equal to 1 by integral part of x? F of x is equal to 1 by integral part of x. This new function here it is to discuss is 1 by integral part of x. So, we have to take enough care that integral part of x is not 0. Well, search for that. When can it become 0? Observe the number line. This is 0. This is 1. What is integral part of 0? 0. Integral part of 0.1? 0. 0.2? 0. like this up to 1 and excluding 1. For all those, integral part is 0 itself. Therefore, this is r minus closed interval 0 to 1, close towards 0 and open towards 1. This is the domain. Why are you deleting this? For any point x here in this interval, integral part x is 0. And we should see that it is not 0 to define f of x. That is why we are deleting interval 0 to 1, close towards 0 and open towards 1. This is also called left closed right open interval 0 to 1. That's all. Well, another function, f of x is equal to log mod x. What is the domain of this function? In what way should you think of? F of x is equal to log mod x. Here, you have to think of two particular things. Number one, basically it is a logarithmic function. Therefore, the quantity present inside this logarithm must be strictly positive. Of course, mod x can never be negative, but there is a little danger. Mod x can become 0 when x is 0. Log 0 also not defined, is also not defined. Therefore, we are supposed to take again enough care that mod x is not 0. So, what should happen? This is r minus 0. R minus 0. For any other real number except 0, mod x is always positive, no doubt about it. Except at 0, mod x is 0. Elsewhere, anywhere else in the set of real numbers, mod x is always positive, and we are able to define log mod x. Therefore, it is the domain. What is the domain? R, that is set of real numbers, minus 0. Well, if f of x is equal to 1 by log mod x, in what way should you consider? Here, two things you may have to keep in mind. Number one, log mod x is defined. Number two, log mod x is not 0. Why? Because log mod x is lying in the denominator. The two things you have to keep in mind. Number one, it must be defined. Log mod x is defined when r minus 0. So 0 is to be deleted from real numbers. Another thing is, this must not be 0. Log mod x is not 0. That is, mod x must not be equal to 1. Mod x must not be equal to 1. Therefore, x not equal to plus or minus 1. Altogether, what are the numbers which you have to delete from the set of real numbers? Minus 1, 0 and 1. If x is minus 1, mod minus 1 is 1, log 1 is 0, 1 by 0 not defined. If x is 0, mod 0 is 0, log 0 is not defined. If x is 1, mod x is 1, log 1 is 0, 1 by log 0 is not defined. So, these are the three troublesome points for us to define f of x. That is why let us discard them. Let us eliminate them from the set of real numbers. So, the domain of the function f of x equal to 1 by log mod x is the set of reals minus the set containing minus 1, 0 and 1. Yes. We shall now see some more examples. Consider the functions e power x, a0 plus a1x plus a2x square plus a3x cube plus etc. an x power n with a0, a1 etc. an belong to R, x belong to R, n belong to n. Mod x, integral part of x, sin x, cos x, sine hyperbolic x, cos hyperbolic x. All these functions have the real domain. In the sense, for every real number x, we are able to define all these functions. These functions are defined on the real domain. For any x, there is no problem at all to define all these functions. So, this is a special case to have a common domain, that is a set of real numbers for all these functions. Another, f of x is equal to root of a square minus x square. F of x is equal to 1 by root of a square minus x square. Let us observe the domain of these two functions at a time. F of x is equal to root a square minus x square is given. What is the domain of this function? For domain of f, what should you require? A square minus x square greater than or equal to 0. That is, x square minus a square less than or equal to 0. That is, x minus a into x plus a less than or equal to 0 is equal to 0. Let us observe the sign pattern. Minus a, positive, negative, positive. To have negative answer, we should have x in the interval. Which interval? Minus a to a. So, what is the domain of the function? Closed interval minus a to a. Closed interval minus a to a. Well, let us consider the same case here. For domain of f, a square minus x square is greater than 0 or greater than or equal to 0. Here, equal to 0 is allowed, but here it is not allowed. As a result, at last we shall be having x minus a into x plus a is strictly less than 0. X minus a into x plus a is strictly less than 0. Thereby, the domain of f is, come on, this is open interval minus a to a. Here it is closed interval minus a to a. In the similar fashion, we will be able to have the domain for root x square minus a square and 1 by root x square minus a square also. Let us write the domain for those two functions now. What is the domain of f of x is equal to root x square minus a square? So, to define it, we must have x square minus a square greater than or equal to 0. That is, x minus a into x plus a greater than or equal to 0. Therefore, by observing the sign technique here, positive, negative, positive, we should have positive answer for x square minus a square. Therefore, the domain of f is equal to minus infinity to minus a union a to infinity. What happens to that case? This closed interval becomes to the open interval. That's all. That is minus infinity to minus a union a to infinity. That's all. That is the domain of that function. Here, minus infinity to minus a closed interval, union closed interval a to infinity. But there, those closed intervals become open intervals because x is equal to a and x equal to minus a are strictly prohibited there to find f of x. That's all the reason. We shall now look at two more functions whose domain is ready to be obtained. Let us see. F of x equal to log of x square minus 3x plus 2 and f of x equal to log of x square minus 1 by log x square minus 3x plus 2. Let us see. To define this, for domain of f, what should we have? X square minus 3x plus 2 is greater than 0 or greater than or equal to 0? It must be exactly positive. Why? Because the function under consideration is a logarithmic function. So, we are not supposed to allow 0 also inside the logarithm. Hence, it must be positive. that is log x square minus 3x plus 2 is greater than 0, thereby x minus 1 into x minus 2 is also greater than 0. By applying the sign concept, positive, negative, positive. To have the positive region, what is the domain of f here? Domain of f is equal to, come on, minus infinity to 1, open interval or closed interval. To decide that, are you allowing 1 or not allowing? No, we are not supposed to allow. If at all, if you allow x is equal to 1, it becomes 0. Log 0 is not defined, that is f of x is not defined. So we are not supposed to allow x equal to 1. Hence, the interval must be open interval 2 to infinity. What is the case with that function? Here, two cases you may have to consider. Number one, first one is log of x square minus 3x plus 2 is defined, and secondly, x square minus 3x plus 2 not equal to 1. That is the enough precaution you have to take. Why? Because if at all this is 1, log 1 becomes 0. 1 by 0 is meaningless. 1 by 0 cannot be defined. Therefore, this is a second precautionary measure. For this, as we could discuss here, x belongs to open interval minus infinity to 1 union 2 to infinity. And for this to happen, x square minus 3x plus 1 not equal to 0. X square minus 3x plus 1 becomes, this side it becomes 1. X square minus 3x plus 1 not equal to 0. It means x not equal to minus b plus or minus root of b square minus 4ac. 9 minus 4 is 5 by 2. Therefore, clubbing these two, the actual domain is open interval minus infinity to 1 union open interval 2 to infinity from this big set minus 3 plus or minus root 5 by 2. That is the domain of the function. That is the domain of the function. These two precautions clubbed together takes this form as the domain of the function. Therefore, as and when that log of x square minus 3x plus 2 is in the denominator, the special and extra matter that you have to keep in mind is you have to take care that the quantity inside the logarithm is not equal to 1 also. Yes, of course, we could have traced this from this procedure. Well, next, let us see one more such example. Let us look at these two problems once again. Here in the first function, f of x is equal to log mod x plus 3. So to define f of x, what are all the precautions that you may have to take? Mod x plus 3 can never be negative, no problem. The only thing that you have to keep in mind is this x plus 3 must not be 0. Why? Because in such a case log 0 is not defined. Therefore, the only precaution here for domain of f is mod x plus 3 should not be 0. That is x plus 3 not 0. That is x is not equal to minus 3. Hence, domain of f is all the real numbers except minus 3. All the real numbers except minus 3. That's all the domain of this. Except minus 3 for any other real number, you will be able to have f of x, no doubt. What is f of minus 1? Minus 1 plus 3 is 2, log mod 2 is 2. What is f of minus 5? Minus 5 plus 3 is minus 2, mod minus 2 is 2, log 2. Yes, it can be defined, no problem at all. What happens to this case? First precaution, what should you take? Log mod x plus 3 must be defined. First precaution. Second precaution, mod x plus 3 not equal to 1. Isn't it? Why are you able to trace this? Because if mod x plus 3 becomes 1, log 1 is 0. The denominator is going to become 0. So f of x is not possible. It is not possible to define f of x. Therefore, to define f of x, the precautionary measure that you have to take here is see that log mod x plus 3 is not 0. That is, see that mod x plus 3 is not equal to 1. That is one of the things that are going to happen. That is, x plus 3 not equal to plus or minus 1. X not equal to minus 3 plus or minus 1. X not equal to, if it is minus 3 plus 1, it is minus 2 or minus 4. Minus 2 or minus 4. Good. So, clubbing these two, domain of f can be written to keep this point in view. What is the number that must be deleted? Minus 3. To keep this point in view, what are the things that must be deleted from the set of real numbers? Minus 2 and minus 4. All together, what is the ultimate domain? Domain of f is equal to r minus minus 4 minus 3 minus 2. Minus 4 minus 3 minus 2. Those are the things. So these are the basic functions on which we are supposed to keep a special eye in estimating the domain. In problems, such simple things might not be given. Log of modulus of x squared minus 3x plus 5 might be given. Log of root of x plus root of x squared plus 3, something like that, such might be given. To trace the answer or to face such type of questions, you must be having some basics. What are the things that must be kept in mind? What precautionary measures are to be taken to define f of x? To have such things in our mind only, we could have discussed all these models. Well, let us turn our head towards some more models in finding the domain. In so many occasions, you may be given a sum of two functions, a product of two functions, a quotient of two functions, or both. In many cases, what happens to the domain of the total function? In such a case, it is of special interest is the case to discuss with them. Suppose you are given a function, say h of x is equal to f of x plus g of x. In this case, what do you notice? You find the domain of f of x and find the domain of g of x also. Then domain of the function h is given to be domain of the function f intersection domain of the function g. That is, if you are given a sum of two functions, even difference of functions, then domain of f intersection domain of g. Not only that, if it is there for f of x into g of x, same thing happens. If it is given as f of x by g of x, a very little change occurs in that case. What is that case? Let us see. If another function, say h of x is equal to f of x by g of x, then another extra precaution is to be taken here in finding the domain of h. What type of that precaution can you guess? It is an easy matter to guess. Why? Because that g of x lies in the denominator you observe. So, additional precautionary measure, what is that precaution? G of x must not be 0. G of x must not be 0. That is, here, to have the domain of h, what are the things to be had? Number 1, find the domain of f. Number 2, find the domain of g. Number 3, find set of all x's such that g of x not equal to 0. This becomes the original domain of h of x. So, what is the thing which occurs on the screen extra? The set of all x's such that g of x not equal to 0, that must also be considered. And intersection of all those three gives the actual domain of h of x. As an example, let us see. F of x is equal to tan x. What is the domain of this? You are asked to have. Tan x is nothing but sin x by cos x. Sin x by cos x. Well, what is the domain of sin x? A set of reals. What is the domain of cos x? Set of reals. So, to have domain of f, what are the things to be obtained? Number 1, domain of sin x, R intersection. Domain of cos x, R intersection. The set of all those x's which are for which make cos x not equal to 0. Yes, you may have to think in a special way. Let us remember, when can that cos x become 0? It's very simple. At odd multiples of pi by 2 only cos x is 0. Therefore, let us avoid those odd multiples of pi by 2 such that x does not take those values. Then cos x is not 0. Therefore, this particular set in the formula, what happens to that here in this case, what happens to that is equal to set of all x's such that x not equal to 2n plus 1 into pi by 2, n belongs to z. Z is sum of integers, of course. Yes, this is the actual systematic procedure. Instead of doing all this, R intersection R is R intersection, that is, you are supposed to take x such that x is not equal to that. So, what does it mean? It is just nothing but R minus set of all 2n plus 1 into pi by 2 such that n belongs to z. Like that, we will be able to have the domain of tan x. As this is the direct example of this concept, I could have consulted with that. Not only tan x, you observe cot x, cotangent of x, it is cos x by sin x. In that particular case, what happens to this set? You have to see that the denominator does not vanish. And in the case of cot x, what is there in the denominator? Sin x. When can that sin x become 0? At n pi. Therefore, we restrict x not to take n pi. Hence, in that case, domain of if f of x is equal to cot x, as it is cos x by sin x, we can trace the answer directly without any manipulation or calculation. It is again, as in that case, r minus n pi such that n belongs to z. This is the domain of cot x. One more thing you can observe. What is secant x? 1 by cos x. The same trouble, same discussion, same calculation, same estimation. Therefore, in the case of secant x also, you believe that this is the domain. So, for both tan x and secant x, this is the common domain. And for both cot x and cosecant x, this is the common domain. Okay, yes. In this way, we speak of domains of some different functions. No doubt, we shall come across some more new functions while solving some numerical problems.